Welcome to Lesson 28, Exponential Decay. Now, in Lesson 27, we talked about exponential growth, right? And if you have growth, it goes up. So this would be growth. Well, now we're getting into decay. So it starts high and it goes low, right? So decay is when stuff goes away. We could talk about snow melting in terms of exponential decay. Well, we could hope that it melts in terms of exponential decay. But you start with a value and it slowly or quickly goes away depending on your decay factor. Okay, so we're on page 251, and we are starting out with a problem. It's going to build to this, but we're talking about the medication cephalexin, or something like that. And we have a problem that says the recommended dosage for an adult is 40 milligrams per kilogram per day, with the divided dosage being given every 8 hours. Well, we've seen these problems before, and if I remember correctly, everybody loved them. So when we look to this problem, we've got a 50-pound kid. And I guess we're assuming that we are dosing the kids the same as the adults based on what's given. So we first need to change our 50 pounds to kilograms. Right, so they tell us that 2.2 pounds is a kilogram, and we know that that makes my pounds disappear. And then we are also told that our dosage is 40 milligrams for 1 kilogram, and that makes my kilograms go away. So I am now at 909 milligrams. So are we going to just shoot this person up with 909 milligrams? No. So we are talking about per dose, and if we go by 8 hours, there are 3 8-hour chunks in a day, so we are going to divide this by 3, and we are getting 303 milligrams per dose. All right, we've done that before. It's a good refresher from the past. Now, moving on to number 2, what does it mean if we say this drug degrades by 50% each hour in the body? Well, if it degrades by 50%, right, it goes down by half. So how much of the drug remains after an hour? Half. So whatever you started with, after an hour, cuts in half. After another hour, cuts in half. So it just continually cuts in half. So when we're looking at this table, we start, as we have found, with 303 milligrams. So when I'm thinking about this, I take my 303 and I'm going to divide that by 2, and that will give me 151.5. And then I take that and I divide by 2, and I get 75.75. And then I take that and I divide by 2, and I get 37.875. And you see the point, the pattern. So right now I want you to hit pause. Complete all 3 of these, because I know that you can find absolute and relative change. And so I want you to go ahead and complete this table and then come back and we'll continue on with this problem. Okay, so if you notice, hopefully you noticed, I rounded in my absolute change column because that was a lot of numbers. But if you notice that these 2 columns, the milligrams of cephalexin left and the absolute change, the only difference is the negative in the absolute change column. And that is because you're cutting it in half. So the difference between what you had before and what you have now is the same as what you have now because you cut it in half, right? And it's negative because it's decreasing. And then you'll notice that the relative change is the same for each. And so that answers question 4. Relative change is the same week to week. And what does the negative relative change mean? Well, hopefully by now this has been driven into your brain that if it's negative, it means we have a decrease. And that makes sense. The drug is leaving our system, so the amount that we have left is going down month to month. Now, what is the percent decrease? Well, if our relative change is negative 0.5, let's change that to a percent and go 2 places. And so we are at negative 50%. Our percent decrease, I guess we could say, is a 50% decrease. Because if you have the word decrease, that implies the negative. And now we are on page 250. Oh, no, we're not. Sorry, I got ahead of myself. The decay factor is 1 minus the percent decrease. So just like with the growth factor, how we added the percent increase, well, because we were getting bigger, with decay, we're getting smaller, so we have to subtract that percent decrease. So we would take 1 minus the 0.5, because we're decreased, and that would give us 0.5. So our decay factor is 50% or 0.5, depending on how you're looking at it. For the model, remember, we want to play with this stuff. And if we're playing with math, we need decimals, not percents. So we would have a 0.5 decay factor for this model. Now, when you look at the stuff in the middle of page 252, you see that it talks about the amount equals the initial amount, and then 1 minus the percent decrease, which we know as the decay factor, raised to the time period. The model is the same as the growth model, except inside your parentheses, you're going to have something less than 1. If you're growing, you're greater than 1. If you're decaying, you are less than 1. So I will have y equals the initial amount times the decay factor raised to the x power. All right, let's start playing with this a little bit. You see the graph of what we just played with Cephalexor here on page 252, and you can see that it goes down. And it starts to go down really quickly at first, and then it kind of tailors off. Because when you are decreasing and you're cutting it in half, well, the bigger the number you start with, the more you're cutting in half at the very beginning. So it makes a little bit of a difference. Now, when we get to the questions here on page 253, and it would be good, again, if you hit pause. I hope you kind of have this down by now, that to hit pause, see what you can do on your own, and then come back and see what's all given in the video. But if you can do it on your own, that's even better. So looking at number 8, what is represented on the x-axis? And then number 9 is on the y-axis. So if we go back to this, here's my x-axis, right? Hopefully you remembered from page 1, we're talking about the hours. And this is the milligrams remaining. So when we're talking about the x-axis, we're talking about hours after consumption. And title of the axis, I would put hours. And for 9, the y-axis talks about milligrams. And for the, the title of the axis, I would put milligrams remaining. Because that's what it's about. That's what it's telling you, after consumption. And you could even put hours after consumption for the x-axis if you like. But for the y-axis, it's how many milligrams are remaining with this drug. So number 10, what is the model for determining the amount of Cephalexor left in the system after T hours for a child who weighs 50 pounds? Well, remember, that 50-pound child gets 303 milligrams per dose. So the starting amount is 303. So y equals 303. We know it's a decay, cutting it in half, so 0.5 raised to the t power. I use t because they asked me to, where t is the number of hours after consumption. So there's my model. And that's kind of the end for this first piece. Now we're going to keep playing with Cephalexor, but we're going to pretend that the decay factor, or that it degrades by 60%. So if you're thinking about it, if it degrades by 60, we would subtract the 0.6. Right, so my new decay factor is 0.4. So instead of 0.5, we're at 0.4, because if it degrades by 60%, that means 40% is still there. So, fill in the table below using the decay factor of 40%. Well, what does that mean? Well, if it's at 40% is still there, that means we're going to take what we have and we're going to multiply by the amount that is still there. So if I take 303 and multiply by 0.4, I get 121.2. So again, I'm going to take, what do I have left, and I'm going to multiply by 0.4, because if it degrades by 60%, then 40% is still there, and now I'm at 48.48. And as I go down, I've got 19.392. I've got 7.76. I'm going to start rounding because it's hard to write in these little things with my fat fingers, and I appreciate you understanding. So you notice how we get pretty low, and it gets lower quicker. Whereas we were not under 1 until 9 hours in the last one, we are under 1 at 7 hours now. So the model for this, we're still starting with 303 milligrams, but now our decay factor is 0.4. raised to the t power. And when would the child need another dose? Now, I'm no nurse, I'm no doctor, I don't know anything about medical. I mean, I pass out at the sight of blood. But what I'm thinking, and I'm using my mathematical knowledge here, sorry that I'm whipping back and forth, they said, this is the first example, they said that they needed a new dose after 8 hours because after 8 hours we were under 1. So I assume that's the reason. So if I give you whiplash and go back here, we would need it when we get under 1, which is after 6 hours. So I think every 6 hours you should get a dose, because that's when you are under 1 milligram remaining in your body. And so in my unmedical opinion, that is where it should be. And of course, I could be wrong. It happens all the time. But that is my opinion. Let's move on to page 254. Here you see we have doxycycline and amoxicillin. Now, I don't really know what doxycycline does. It uses to treat Lyme disease, as does amoxicillin. Who knew, right? This is what you can get if you read in this packet. Some interesting knowledge that you may or may not have had. So, when we're looking at this, we are going to use this data to kind of figure out, I don't know, everything we want to know about the world. And one thing I want to point out to you is that hours since the last dose. So this is the initial amount. Notice how much each one starts with. That'll make a difference in their initial problem. We will also pay attention to, what's the word I'm looking for? To find the growth factor. Remember how we put things on top, or not multiplied, we made a ratio, new over old. Same concept here with the decay factor, which we'll get to in a minute. So, recommended dosages for amoxicillin. Well, that's the kind of the first piece. Amoxicillin starts with 500 milligrams, so that's the recommended dose. And for doxycycline, it starts at 100 milligrams. So those would be the first pieces if we're writing models. Now, how much has amoxicillin degraded from hour to hour, and what is the decay factor? So if you just look at the first two, right? So at 0, we're talking about amoxicillin, crapola. That would be a 500, and at 1, we're at 250. So if we think new, old, if I put new over old, just like we did with the growth factor in the last lesson, I get 0.5, right? So my decay factor is 0.5. Now, when you look at how much doxycycline has degraded, well, when it was 0, we were at 100, and at 1, we're at 70. So new, old, if I put my new over old, I get a degrade factor of 0.7. Okay, so we are at 0.7 for my decay factor. So now that I have those, I can say determine the exponential decay equation for amoxicillin. Well, for amoxicillin, we know we started with 500 milligrams. We know our decay factor is 0.5, and we're going to raise that to the x power. So there is where x is any hour past the initial dosage, and y is how much amoxicillin is left in your body. F is similar in terms of doxycycline. We start with 100. Our decay factor is 0.7, and it's raised to the x hour. Again, where x is any hour past the initial dosage. I'm skipping letter G because I'm not really sure how to answer that. Again, I don't have any medical expertise. I don't know what it means for drugs to stay in the body or anything like that. So because I don't have any expertise, I am not going to answer that. That will be a good question in class for us to kind of have a discussion of what people think. But for me to tell you in the video is not acceptable in my opinion. So we're going to move on to page 255. And I would like you to hit pause and try as much of this page as you can, and then come back and watch the explanation for those. So here in number one, a $22,000 car depreciates by 12% per year. Determine the model. Okay, well, we've got to deal with our depreciation. So 1 minus the depreciation will give us 0.88. So right there is my decay factor. So when I'm writing my model, I start with $22,000. It depreciates, right? Well, I guess it depreciates 12% a year, which means 88% is still good. Raised to the x power, where x is, it says t years, my bad. So we'll make that a t, number of years past purchase. Now, using that model, how much will the car be worth in 4 years? Well, it started at $22,000. 88% is good after every year, so if I raise that to the 4th power, after 4 years, your car would be worth $13,193.30. Now, I would like to make just a statement. That's assuming that you don't wreck it, trash it, put 800,000 miles on it in 4 years. But there are a lot of other variables that go into the value of cars. But years since purchase are definitely one of them. Number 2, high-def TVs are averaging $1,500 currently, but costs are decreasing at a rate of 15% per year. How many years will it take for these TVs to be as low as $500? All right, so again, just like in the linear modeling section, if we want to predict for the future, we have to have a model. You can't just make up stuff. You've got to have a model to use for predictions. So I'm going to start by saying I know that they're decreasing at 15% a year. So 1 minus 0.15 gives me 0.85. There's my decay factor. So my model is I start with 1,500, I've got 0.85, and I'm raised to the x power. So now I can plug values in and see what we've got. So, if I plug in, let's say x is 6. Well, after 6 years, after 6 years, the value of the TV would be $565.72, I think, if I can read my handwriting. So we are not quite as low as 500. We're at 565. So let's go another year. Let's ramp it up to 7. Well, after 7 years, the TV will be at about $480. So because after 7 years, it's at $480, that's how long it'll take. So if you're waiting until the TV is only $500 so you can buy it, you're going to have to wait 7 years to do that. Okay. Well, at least that'll give you plenty of time to save your money. And number 3. I like number 3 because it kind of shows the difference between increasing and decreasing, right? Classic cars increase in value. And these are classified classic cars, not cars that you think are classic because you've owned it so long. Whereas some cars decrease in value. So we've got a 2014 Mazda Miata, sells for $23,000, depreciates 10% a year. And a 1970 Ford Mustang, it's only worth $12,000 right now, but it's increasing in value by 6% a year. So write equations to model the value of each car over time. So I'm going to put the Mazda over here, and I'm going to put the Ford over here. So hopefully the Mazda, right, it depreciates. That's 1 minus 0.1. So it starts at 23,000. Because it depreciates, it's going to be less than 1. And X represents the number of years. Now for the Ford, right now it's increasing. So because it's increasing, we're going to add the 0.06. So it starts at 12,000, and we've got 1.06 raised to the X power. And that is an ugly looking 0. So 1.0. Okay. So you can see how decay factor less than 1, growth factor greater than 1. A little bit of a difference. Now, use each equation to estimate the value of the car over the next 6 years. Now, I'm going to do the first Mazda Miata together, and then I want you to do the rest of them for both for each car. So, for the Mazda and the Mustang. So, we want to know X is 1, X is 2, X is 3, X is 4, X is 5, and X is 6. We want all of these so that we can see the value and how it changes year to year. So, when X is 1 for the Mazda Miata, I'm going to take 23,000 times 0.9 raised to the first power, and I'm going to get a value of $20,700. Okay, so I want you to finish out the rest of these. Now, similar with the Ford, we want X is 1, X is 2, 3, 4, 5, and 6. So for 1, I would take 12,000 times 1.06 raised to the first power, and I'm going to get an answer of 12,720. So you can see that after year 1 with the Ford, it goes up. After year 1 with the Mazda Miata, it goes down. So finish each of these and then come back and check your answer. All right, so here are the rest of the values for the Mazda Miata. So you notice after 6 years, you're down to a value of about $12,000. So in those 6 years, you have decreased, a little over $10,000 in terms of the value of your car. And if you look at the Ford Mustang, after 6 years, you've increased your value just a touch over $5,000, and you're up to $17,000. So when you look at question C, at what point in time will the value of the Ford Mustang exceed the Mazda Miata? Well, year 4. Because in year 4, the Mazda is at $15,090 and 30 cents. That's the Mazda Miata. And the Ford Mustang is at $15,149.72. So it's not a big change, but in year 4, that's when it switches and the Ford Mustang becomes more valuable. So that is exponential decay. I hope you enjoyed it, and I will chat with you later.